Chapter 46, Particle Physics and Cosmology. After nearly 2 years of studying introductory physics, we've now come to the final chapter, the grand finale. To some of you, this could be the last chapter of physics that we'll be studying as a separate course. And you hear the phrase going out with a bang. And here in this chapter, we're going to literally do that or literally study that. We're going to study the Big Bang of the universe, among other things. This is true grand finale. This is where we do things that we can only be done in physics. And that is, we're going to see how the world of the ultra small meets the world of the ultra large. And also we're going to tie time scale together as well. In this chapter, we're going to look at how really small particles whose size are below 1 Fermi or 10 to the negative 15 meters, and how the world of very large, the size of the observable universe, which is greater than 10 to the 26 meters, behave, and more interestingly, more astonishingly, I should say, how the world of very small, these particles, can affect the fate of the very large, the entire universe. So we see the very small and very large, they're actually tied together in an intricate way, and this can only be seen in physics. No other science will encompass this many orders of magnitude in size, and indeed, we're also going to probe deep into the past. The age of the universe in today's theory is believed to about 12 to 15 billion years old. So we'll take a step back, way back in fact, and look at the early state, this early state of the universe, according to the Big Bang theory. And this chapter is divided into 2 parts, the particle physics part and astrophysics part. In the particle physics part, we're going to look at the fundamental forces of nature, or otherwise known as fundamental interactions, and the particles that participate in the fundamental interactions. These particles are the building blocks of nature. And when the particles interact with each other, they have to follow what's called conservation laws. We know conservation of energy, momentum, and angular momentum, right? These are not the only conservation laws. There are others we have to observe. And we'll also look at particle models, how you classify these particles, how you simplify the way the particles come together. Are there particles that are more fundamental than others, and so on? We'll see that. And in astrophysics, basically 2 things. One is we're going to look at how star systems evolve, how stars such as our sun evolve, the evolution of the stars and galaxies. Also, on an even grander scale, we're going to look at the evolution of the universe, starting from the Big Bang theory of the universe, and that is a branch of astrophysics called cosmology. So, we're going to start with our discussion of particle physics first. The first thing I want to talk about is the concept of antiparticles. Antiparticles are just like particles, except they have opposite charges. That was the original idea, was proposed by Paul Maurice Dirac, a brilliant British physicist, who also gave us the Dirac delta function and many other contributions in quantum mechanics. What he did was he combined relativity, Einstein's theory of special relativity, and quantum mechanics together. So he pretty much studied the so-called relativistic quantum mechanics, in which the Schrödinger's equation is to be replaced by the Dirac equation. We're not going to get into the details of the Dirac equation, but among the features of the solution to the Dirac equation is what's called a negative energy state. What's a negative energy state? Well, when you look at the energy momentum relationship, E squared, that's in relativity, okay, not in conventional low speed case where Schrödinger's equation holds. E squared equals P squared C squared plus M C squared, the whole thing squared. Remember that? Normally, we get E from it by taking only the positive square root. We discard the negative answer. But mathematically, of course, there are 2 solutions, positive and negative square root of P squared C squared plus mc squared and then squared, right? We usually discard a negative sign, but it turns out according to the Dirac equation solution, the negative sign actually means something. You cannot just throw it away. And you have here this plot, okay? The energy is positive, negative. P itself is the momentum, and no matter what P is, P squared term is always positive. So the energy of the particle is actually divided into two regions, a negative energy part and positive energy part. You set P equal to 0, and then when you choose the positive energy, then the smallest value you get is mc squared, so it's mc squared and up. And when you choose a negative branch and you set P to be 0, then you get the top of the negative energy region, which is negative mc squared. And when you add momentum, it's going to go further down. So you see there's a gap. Okay, there's a gap. And this thing looks kind of like the energy gap that we studied in semiconductors, right? Even though it's a totally different thing, all right? You have here some sort of forbidden gap between the the top of this energy band and the bottom of that energy band. Even though this it's not quite a very good analogy, but something similar to that was that in the case of the semiconductor particle, semiconductor physics, this band was completely filled. That one was completely empty when the temperature is low. But I can give this system some energy through either thermal excitation or giving it a photon, and that can bail an electron out from here to there. And as a result, both of these bands can now contribute to electrical conductivity, because this is partially empty, leaving what's called a hole, and here is partially filled with leaving you have electrons doing conduction. What we have here is something very different. This is, according to the Dirac equation, the allowed energy solution for a free electron. And again, the negative energy states were usually discarded because we say, how does that make any sense? You have negative total energy. But according to Dirac, it actually meant something. Usually, according to Dirac, this entire electron C, so sort of what's called electron C, is entirely filled. It's like a totally filled band, which does not contribute to electrical conductivity. You do not see these electronic states. Electrons cannot just go from one place to another because of the Fermi principle. All these states are filled. They cannot do anything. But once you have enough energy to bail an electron out across this gap, which is 2mc squared, then you're going to leave a hole behind, and you could get this electron. And this hole is is equivalent to a positively charged electron going backwards, just like the whole idea in semiconductor physics. So according to him, once there is a vacancy here, this becomes observable. It is called a positron because it's like a electron with opposite charge moving backwards. So according to Dirac, the positron should exist, and the incoming energy which lifts it up should have the energy of at least 2mc squared. mc squared is about half an MeV. So therefore, you need at least 1 MeV. This kind of photon is in the gamma ray range. So it is possible to have a photon in the gamma ray range, liberating an electron from the Fermi C all the way across the gap. So you get E minus, what's left is E plus. That is what's called a positron. That is according to the Dirac's theory. And even though the idea sounds crazy, the positron was actually observed later. So the Dirac theory turned out to be correct. It gave a correct prediction of the existence of a positron. According to modern theory of QED, quantum electrodynamics, which is after the Dirac's prediction of positrons, all elementary particles, electron only being one of them, all elementary particles, each of them has its antiparticle. The antiparticle should have the same mass, okay, but opposite electrical charges, and some other opposite quantum numbers, such as Bion number or strangeness or lepton number, those things which we'll study later in this chapter. So the antiparticle is not unique to the electron, and even the charge neutral neutron has an antiparticle, and even the charged neutral neutrino has an antiparticle. Of course, being charge neutral, the antiparticle has the same charge as the particle itself because they're both charge neutral. Okay, Q equals negative Q. But there are other characteristics that are different. There are different, for example, baryon numbers and lepton numbers and so on, which we'll see in a minute, which distinguishes these two particles. So anti-neutron and neutron, they're not the same thing. Among other things, the anti-neutron has an opposite magnetic dipole moment as the neutron. Okay, so this is an event where a gamma ray photon can generate a pair of electron-positron. The opposite process of an electron-positron pair decaying into gamma rays has also been observed, except in this case, it turns out we need two gamma rays. We need two gamma rays. One single gamma ray photon will not work. This is a matter of conservation of linear momentum. Because if you had only one single gamma ray photon, what is the problem? Well, remember, gamma ray photons, just like any other photon in vacuum, travel at the same speed of light, no matter who's looking at, whatever reference frame, right? How about if we choose the reference frame, which is the center of mass of these two particles to begin with? Okay, so in this reference frame, which is the center of mass of these two particles, what is the total momentum before the collision, before this process? That's zero, right? Because the center of mass doesn't move, right? So the momentum before the collision is zero. The momentum after collision, if there is only one single photon, this photon has to travel at the speed of light, no matter which frame, including the center of mass frame. And therefore, after the collision, after the annihilation, the single photon will carry momentum because it travels at the speed of light, even in this reference frame. And therefore, you have zero momentum, but non-zero momentum afterwards. That doesn't work, does it? So therefore, how do you deal with that? You generate two photons traveling in opposite directions. So their momentum cancel out. That's how you preserve conservation momentum 0 to 0. Okay, so this is the event that's positron and electron-positron annihilation. Here you have electron-positron creation, in which a single photon will actually do. All right, so you have this positron, which is probably the most famous of all antiparticles. Positrons can be used in many ways, including medical application. There is something called the PET scan, positron emission tomography. Positron emission tomography. It is very useful at detecting early stage cancers. You can use it as a whole body scan, and the way it does, the way it functions is this: the patient is first of all injected a glucose solution, which is infused with some trace amount of radioactive nuclides, which will decay by emitting positrons. Okay, these positrons, once they get loose, they are almost immediately captured by some electrons because there's so many electrons nearby in molecules and atoms, and as that happens, they're going to emit two gamma ray photons in opposite directions, and these gamma ray photons are captured by detectors, one going this way, one going that way, and then the detector can pinpoint where that event took place. Okay, which part of the brain, for example, had this event. Now, the glucose wants, for some medical reasons, they are more likely to congregate where the cancer cells are. This is where the metabolic rate is higher, and metabolism involves the consumption of glucose molecules. So this is where these radioactive traces are more concentrated, and so you see more decay events around the cancerous region. This is a highly sensitive technique. You can use that to detect cancer cells, cancer growth that's too small to be seen with naked eye. If anything, it often produces false positive results because of ultra sensitivity, but again, it's extremely sensitive, so it's very difficult to miss anything even very small. It is a very expensive technology because of the gadget being used, but again, it is very valuable at detecting early stage cancers in various parts of the body. Before we get to the details of how many fundamental particles we have, Let's look at what's called fundamental forces, because different particles will participate in different fundamental forces or interactions. There are only four distinct types of fundamental forces. Things like friction, for example, is not a fundamental force. Rather, it is a manifestation of one of the fundamental forces, which is the electromagnetic force. When the molecules and atoms get close together, they can interact electromagnetically, creating friction. There are four types of truly distinct fundamental forces: strong nuclear force, electromagnetic force, weak nuclear force, and gravitational force. And they each have relative strength, range, and so on. Let's see here. The strong nuclear force, that's what binds the nucleons together, among other things. It is a short-ranged force with a range of only 1 Fermi, but it has the strongest strength, which is labeled as 1 unit here. Relative to that, the electromagnetic force is 2 orders of magnitude lower than that, but it's got an infinite range. Okay, the weak force, we call it the weak force because it is indeed weaker even than the electromagnetic force. It's 3 orders of magnitude weaker than that. It is involved in it is involved in things such as beta decay. It is involved in it's generally considered also as a nuclear force. Now, the gravitational force is the only universal force because the only thing it takes is mass. As long as you have mass, you have gravitational force. The gravitational force is the weakest of them all. It's 10 to the negative 39 compared with the strength of the strong nuclear force, but also get an infinite long range. And these forces have different functions, okay? They have different realms of dominance. If you look at something extremely small, we're looking at 1 Fermi or less, then the strong force takes over. It's the strongest of all forces. The weak force has an even shorter range, and it is involved in certain type of reactions such as beta decay. Both of these are considered nuclear forces. The electromagnetic force, even though it's weaker than the strong force, it's got an infinite range. This is what's tying atoms and molecules together to form the atoms to form molecules, the molecules to form solids and liquids and so on. So that's very important, of course. And the gravitational force, on the other hand, is the weakest of all forces, but it is the dominant force on large scale matters, such as the force between planets and stars, and it's also what's holding galaxies together. It is the dominant force on large scale, in the universe, basically, any large scale objects. And all these forces realize the interaction through what's called mediating field particles. Mediating field particles. All these field particles are bosons, it turns out, so they're also called gauge bosons. This one is familiar, photons. Photons mediate electromagnetic interaction. What do I mean by mediating electromagnetic interaction? It turns out that the way 2 electrons repel each other, or the electron and photon attract each other, is by emitting and absorbing what's called a virtual photon. Virtual because it's not observed before it just disappears. Okay, and the nuclear force, the strong force, is because the particles involved in strong force exchange what's called gluons, and so on. And the graviton is supposedly the field particles that mediate gravitational interaction. So 2 masses interact gravitationally by exchanging what's called graviton. This has not been observed, and they have drastically different masses. You can see here, drastically different masses. These 3 have no mass at all, but the weak force, even though it's quite weak, the force, the particles that mediate weak force is extremely massive. We're talking about 80 to 91 GeV. GeV is 10 to the negative 9 eV. These particles are extremely massive, and guess what? They have been discovered. Not very long ago, but they have been discovered. These are real particles. Okay, we'll talk more about those things a little bit later. Now let's first examine the idea of interaction through exchange of a particle. This is the interaction mechanism for all these 4 fundamental forces. And to help us illustrate this process, we use what's called a Feynman diagram. The Feynman diagram was invented by the great Richard Feynman, one of the most brilliant physicists of the 20th century, who used to teach at Caltech just down the street. The Feynman diagram itself, when you draw the Feynman diagram, it actually involves complicated rules. Each line here actually represents some mathematical formula. It actually is something you cannot just draw arbitrarily, but it is also very, very useful in popular culture and for popular science, because it gives us a visual idea. Even though we do not really go beyond that, we don't look at what this line really means. It actually means an integral, but we don't go that far. We just look at the illustrative purposes. You see, we have a proton and a neutron. They attract each other if they get close together by about 1 Fermi or so. That's a strong nuclear force, right? How is that force realized? Well, it turns out that the neutron gives the proton a pion, which is this mediating particle, and as a result, you have this interaction. Okay, this is an attractive interaction. So they exchange this particle called a pion. That's how their interaction is facilitated. That's how they get an attraction. And another example is in the weak interaction. Electrons interacting with a neutrino. These are the electron neutrino, by the way. The weak interaction takes place in a much shorter range. We're talking about 10 to the negative 3 Fermi. This is 1 Fermi. Here is 1,000 of a Fermi, and they exchange a very heavy particle called the Z particle. The Z particle has an astonishingly large mass of 91.2 GeV, even though it exists only for a very small fraction of a second. This was discovered in 1983. The pion was discovered in 1947, both following theoretical predictions. And here is yet another example. Strong interaction, weak interaction. This example is electromagnetic interaction. Electrons repel each other by exchanging a virtual photon. And this we'll talk about in the next page. So you see, this is how we use an illustrative diagram called Feynman diagram to show how the process goes on as a visual picture. But again, the Feynman diagram itself, there are stringent rules on how to draw each line, what each line actually represents. That's something we do not discuss here in this course. But let's take a closer look at how this mediation particle behaves, what kind of mass it has, and so on. Historically, the first person who gave us the idea of two nucleons exchanging a particle so that they can attract each other was by the name of Yukawa. Yukawa was a Japanese physicist who proposed that a particle called a meson must be exchanged between the two nucleons in order to facilitate this nuclear-nuclear interaction or attraction. Yukawa proposed that in 1935, and he even gave an estimation, a good estimation, as to what is the mass this meson should be. So here, let's do an estimation of what kind of mass this particle must have that facilitates the interaction between the two nucleons. The two nucleons have to get close enough, about 1 Fermi, so D is about 1 Fermi. Okay, so during that time, when they get that close, a meson called a pi meson is emitted by one of the nucleons and travels to the other. Let's say it travels at the speed of light. That's as fast as it can go, okay, or near the speed of light. The time it takes to go from here to there, therefore, is d over c. This is the time during which this pi meson existed. After that, it's been recaptured by the nucleon, and it disappears. Okay, so this delta t. Now, how much energy should this pi meson possess? We don't know for sure, but we do know that the uncertainty in the energy of this pi meson, delta E, must relate to delta t by this. Delta E times delta t is of the order of h bar. That is the uncertainty relation between energy and time, the Heisenberg uncertainty relationship. Okay, because you exist in such a short period of time. Delta t is extremely small, which means that I can pinpoint with very good accuracy when you existed. And as a result, delta E must be very large because, if you know one accurately, you lose track of the other one. So delta E must be very large. There is a very large amount of uncertainty in its energy, which means the energy cannot be very small either, because if the energy is very small, how can you measure, suppose you measure a million times, how do you get very, very different values? It's impossible, because the energy is, if it's always very small, you're always going to measure only over a small range, right? So as an order of magnitude, we say the uncertainty in energy of this particle has the same order of magnitude as the energy of the particle itself, which is mc squared. That's correct in order of magnitude estimation. So mc squared is of the order of h bar over delta t. That is just delta E, h bar over delta t. And delta t, again, is the time it takes for the meson to start from here, end up there, which is d over c, right? Okay, flip that c over, you see the familiar h bar c, which is 197 Fermi MeV. Divide by the range d, which is about 1 Fermi, you get yourself about 200 MeV. This is a reasonable estimation as to the mass of this pi meson must have. That was proposed by Yukawa in the year 1935. The pi meson was not discovered until the year 1947, and in between those, scientists were looking for this very actively, so they found a particle with a mass which is about 106 times the mass of the electron, actually 106 times MeV. They thought it was the Yukawa meson, but it turned out that was not. It was the muon, which is a fundamentally different type of particle than the meson. The meson was discovered in 1947, and Yukawa won a Nobel Prize for his work. We call it a meson because it came from the Greek word meso, which means in between, because the mass of the meson is somewhere in between the electron and the nucleon, which is, the electron is half an MeV, nucleon is about 1,000 MeV, this is about 200 MeV. Okay. Now, here is another Feynman diagram representing the process of a neutron decaying into a proton plus an electron plus an anti-electron neutrino. Okay, this is a weak interaction. This decay is by weak interaction. Weak interactions typically execute much slower than strong interaction, and the Feynman diagram illustrates the process. The neutron emits a field particle called W negative. It carries negative charge, so the neutron itself now turns into a proton, positive charge. That's conservation of charge. And this field particle exists for a very short period of time, and then it decays further into an electron and an anti-electron neutrino. That's the final product. Okay, this process is extremely brief. Now, the problem with this diagram, and even the problem with the meson, the Yukawa meson, the very original one, is that it seemed to have violated conservation of energy. Why? Because you have a proton, a neutron, neutral proton, whatever, they have roughly the same mass, right? The difference in mass is only about 1 MeV, even if it's a proton neutron. If both are neutrons, the same exact mass. But during that very brief moment of time, d over c, no matter how brief it is, during that time, you had an electron here, you had a nucleon here, but you also had a pi meson in between, didn't you? You had a pi meson in between, right? The pi meson is not massless, it's carrying a significant amount of mass. Okay, it's about 1/5 of the mass of each nucleon. So it seems that for this brief moment, we have violated the conservation of energy. We added energy to the system by about 20% in this case. And in the case of this W boson is a lot worse than that, because the mass of the starting particle, the neutron, is only 939 MeV. It's under 1 GeV. Okay, 1 GeV is 1,000 MeV. And yet, the W meson is extremely massive, 80.4 GeV. So you're getting an intermediate particle, you're emitting a particle with more than 80 times the mass of yourself. How does that work? How does that work? You even get yourself, a proton back. This is not a violation of the conservation of energy, because we have the Heisenberg uncertainty principle. The deal is, the weak interaction happens over an extremely short range. The strong interaction is about 1 Fermi. The weak interaction is 10 to the negative 3 Fermi. Okay, it's 1,000th of the range of even the strong interaction. And so therefore, even if the this particle travels at the speed of light, it can only exist for a very, very brief moment. What kind of brief moment we're talking about? C delta t. Delta t is 1,000th of that, because this d is 1,000 times that distance traveled. So you can estimate delta E for this W meson using the same formula, except that d is 1,000th of a Fermi, not one Fermi. And therefore, you have to add 3 orders of magnitude to this guy. All right? 3 orders of magnitude to this guy. So we're not looking at 200 MeV, we're looking at 200 GeV. So no wonder, you can permit a lot of mass here, because it's the uncertainty relationship involved. But at this point, this guy is gone. Okay, this guy's gone. So the final product certainly have conservation of momentum, no problem, because this neutron has enough mass to give this one plus some energy. Okay, so this is how we do not violate the conservation of energy, even though a very massive particle can exist for a brief moment. That's the Heisenberg uncertainty principle at work.